Welcome. One of the nice things about the Earth is that it has mountains, plains and deep oceans. It has a topography. We at Delft work in all these domains. Elevations can change over very short distances. In places like the Apuane Alps or Tuscany, peaks higher than 1500 meters are at few kilometers from the sea. Snow in the morning, afternoon on the beach. The diagram on the slide shows the percentage of the Earth's surface on the horizontal axis, which lies at a certain altitude indicated on the vertical axis. You can see that something like 30% of the Earth's surface lies at around 500 meters. An even larger portion of the Earth, nearly 50%, lies at around 4 kilometers beneath sea level. Why are only few regions very high and a lot of regions close to sea level? Topography is essentially controlled by isostasy. Isostasy is not much more than the law of floating bodies described by the Greek philosopher Archimedes more than 2000 years ago. Archimedes discovered that the weight of a floating body is equal to the weight of the displaced fluid. Here you see the mathematical formulation of Archimedes' law. Setting the weight of the floating body equal to that of the displaced fluid, you can extract h, which corresponds to its height of the top of the block above the fluid. In the real world, this would be the topography. As you can see, the only terms which are in the equation refer to the height of the block and the densities of the block and the displaced fluid. In other words, what happens below the base of the block is irrelevant. We define then a compensation depth, which is the surface separated domain with low changes from the one where no changes exist. An alternative formulation of the law of isostasy is that if isostatic equilibrium exists, then the weight of all columns above the compensation depth are the same. There are then three parameters controlling the topography of our block: the density of the block itself and of the displaced fluid, and the height of the block. In the upper part of the slide, you see that the higher the density of the floating block, the lower its topography. Indeed, heavy body tend to sink, decrease in the topography. A decrease in thickness of the body produces the same result, namely a lower topography. Note also that the base of the thin block is higher than that of the thick block. But what does the floating block correspond to in the Earth? And the liquid? We answer this question looking back at the outer part of the Earth and searching for the part of the system which is more likely to behave as a fluid. Will this be the crust? Probably not. The lithospheric mantle? Surely not, as it is composed of very strong minerals. What about the asthenosphere? Yes, the asthenosphere is hot, has a small portion of melt, and can flow more easily than the overlying layers. Never forget that we are talking of flow at solid state, comparable to that of ice. The floating block is the lithosphere. The fluid is the asthenosphere. Let us look at the density of the floating block, the lithosphere, and of the displaced fluid, the asthenosphere. The simple fact that we are standing on the lithosphere implies that its average density is lower than that of the asthenosphere. But we know that the lithosphere is composed of two layers with very different densities. The crust is composed of low-density rocks and the lithospheric mantle made of heavy rocks. You can see representative values in the slide. The key observation is that the density of the crust is the lowest of all, and on the other side, the highest density is that of the lithospheric mantle. Like a piece of wood attached to steel, it is the crust which keeps the lithosphere afloat. Now let us go back to geology and consider a typical passive continental margin. Isostasy is able to explain most of the first-order topography you see. Representative densities values are shown in the picture. On the left side of the picture, you have a thin, heavy crust underlain by a thin and heavy lithospheric mantle. No surprise that the top of this block will be very low, below sea level. On the right-hand side of the picture, on the contrary, you see that the lithosphere is composed of a thick, low-density layer overlaying the mantle. Obviously, this results in a very high topography, the mountains, and a deep root. Amazing how a simple relationship like the one proposed by Archimedes 2,000 years ago can explain the topography of the Earth. The Earth is not static. Mountains rise and subsidence occurs, allowing for the accommodation of kilometers of sediments. How does this work? Our discussion of vertical movements is based on the principles of isostasy. We state that in conditions of equilibrium, the weight of the lithospheric column above the compensation depth must be the same everywhere. In other words, topography is a function of the weight. If the thickness and/or density of the lithosphere changes, then vertical movements are expected. The most common way to change the weight of the lithosphere is by extension or by shortening. By extension, the lithosphere will tend to become thinner. By shortening, it will become thicker. In the following, we will only look at what happens with extension. Applying the same rules, you can easily predict what happens during shortening. The following discussion is somewhat complicated, so I need all your attention. This is how we will do it. We will look separately at the behavior of the two fundamental components of the lithosphere, namely the crust and the lithospheric mantle. For each component, we will look at the vertical movements during and following extension. At the end of the clip, we will integrate the two components, predicting vertical movements of the Earth's surface in rifty basins of different characteristics. The crust is the easy bit. During extension, the crust will become thinner. In terms of isostasy, thinning of the low-density layer imposes downward movement and the surface of the Earth will subside. After the end of extension, no thinning takes place anymore and no vertical movements are predicted. The behavior of the lithospheric mantle is more complicated because its lower boundary is an isotherm and not a material boundary as the moho. The result is that vertical movements will depend on how fast thinning occurs. At the beginning of the experiment, the isotherms of the LAB are flat, and we consider the evolution of a rock initially situated at the depth of the 1300 isotherm. During thinning, the rock will move upward, for instance, of 30 kilometers, and will then end up at 90 kilometers depth. The question is then, what temperature will the rock have when it reaches its final depth? If the movement is very slow, the rock has all the time to adjust its temperature to that of the surrounding rocks, and when at 90 kilometer depth, will have a temperature of 1300 degrees. This means that the isotherms will not move. Because the moho has moved upward, slow movements result in the thickening of the lithospheric mantle and, therefore, generalized subsidence. Following the end of extension, the flat isotherms will remain flat and no vertical movements are expected. If, on the contrary, movement is very fast, the rock cannot equilibrate and will preserve its initial temperature of 1300 degrees during movement. This means that the 1300 degrees isotherm will have experienced substantial displacement, creating a large thermal anomaly. The thickness of the lithospheric mantle will not change or might even decrease. This will translate in little vertical movements, maybe even some uplift. Following the end of extension, the thermal anomaly will not be supported anymore by extension and will decay. The lithospheric mantle will become thicker and subsidence will take place. This despite being after the end of rifting. Let us now put together the behavior of the crust and of the lithospheric mantle. First, in the case of slow rifting. During thinning, the crust will always want to create subsidence. If extension is slow, further subsidence will be added by the lithospheric mantle, resulting in very important downward movement. Following the end of thinning, nothing will occur. If extension is fast, then the subsidence imposed by the crust will be partly compensated or even overruled by the lithospheric mantle. Important, posterior subsidence will take place when rifting was fast. Yes, I admit predicting vertical movements is not always easy, but it's important and is needed to understand the formation of mountains and basins.